In this video series, we are going to learn Monte Carlo simulations from the very basics. Okay, so over the next few months, I'm going to add a number of videos to this playlist. We'll start with very simple examples so that we can understand the basics, and then we will learn how to apply the Monte Carlo simulations to real life use cases like stock price prediction, portfolio optimization, the risk prediction, maybe to understand some material properties, etc. Right? So I will add more and more real world use cases in a few months. But in the next few videos, we are going to learn the very basics of Monte Carlo simulations. Okay. Now, in our real life, whether it is personal or professional life, we often ask questions like, what are all the likely possible outcomes, and among those one, which one is the most possible outcome, right? So Monte Carlo simulations, it tries to answer the same questions. Now let's take an example. So let's say here we have an outcome y, which is dependent on a number of variables like x1, x2, x3, and xn. Right? Now we are interested in what are all the possible outcomes for y given these input variables. Okay. Now what we do in simulations is we try to design this virtual experiment. We call it virtual because we will be performing this experiment on a computer. Okay. Now, okay, let's take this example so that we can understand easily. So let's say we are trying to predict the number of sales next month. Now we are keeping all other external variables fixed except these three. Let's say the number of customers, the interest rate, and the number of new products next month. Okay. So our sales for next month are going to be dependent on only these three values next month. Okay. Now let's say we already know the functional form. So for example, given these three values, we know how to compute the sales for next month. But even then, the uncertainty comes because these three input variables themselves have some uncertainty in them, right? For example, let's take the number of customers. Let's say we have currently 1000 customers. Now every month we are going to have 5 to 10 customers increase, right? So next month we may have 1005 or 1006 or 1007 or even 1010, right? So our first variable number of customers itself, we have a range, right? We don't have a single number. We have a range, or we have a known probability distribution based on the historical data. Now similarly, the interest rate. Let's say the current month interest rate is 5%. The government might increase the interest rate next month by, let's say, 0.5 points. Now it may increase, it may not increase. But let's say we know we are 75% confident that they don't increase, but there is 25% chance that they will increase by 0.5 points, right? So our second variable, interest rate, can also be either 5 with probability 75%, or it can be 5.5 with probability 25%, right? And finally, our third variable, number of new products. Okay, let's say the current month we have 10 products, and let's say every month we will be launching 1 to 2 new products. So we may launch one product or we may launch two products. So next month we may have 11 products or we may have 12 products. Let's say they are equally probable. So even for this simple problem with only three variables, each variable has its own distribution, right? With different values with different probabilities. Okay, so that's where the uncertainty is coming from. Now in simulation, what we do is we repeat the experiment many number of times. So the first experiment is, given that we know the value of number of customers is going to be between 1005 to 1010, what we do is we pick one value. We randomly pick one value from this probability distribution or the range, the likely range, right? So we pick one value for number of customers. We pick one value for the interest rate. We pick one value for the number of new products. It can be 11, for example, right? Now we have 3 exact values for these 3 variables. Then what we do is we plug in this function. Let's say that we already know the functional form. We compute the number of sales next month. Okay, so we did one experiment. We have one outcome or one value for the sales next month. Then what we do is we pick one more value for each of these 3 variables. Okay, again from the known range or the known distribution. So we draw 3 values for these 3 variables. We again compute the sales for next month. Okay, so we have the second value for the sales next month. We repeat this experiment many number of times. In the next couple of videos, it will be clear to you why we need to repeat this experiment so many number of times, even millions of times. After we repeat the experiment, let's say 1 million times, we will have 1 million values for the sales next month. Okay, then we use those 1 million values to find out again the distribution of sales next month. From the distribution, we can find out what is the most likely number of sales and how confident or how likely that to happen. Okay, I hope that concept is clear. But again, we are going to see a number of very simple examples so that it will be clear to you. Okay. Now, here I have listed few applications, but as I was saying, Monte Carlo simulations, they have applications in every area one can think of. Okay. Now, we discuss this. For example, in this artificial intelligence space, the 2 areas where they are mostly used are this optimization and search, right? For example, we can have millions of outcomes for a given problem, right? And when we search through that millions of outcomes, it's impossible to visit assess each outcome, how likely it is possible, right? So Monte Carlo simulations, they can guide us to the most probable outcome in a few steps. Okay. And so the simulations, they depend on we need to understand or we need to have good understanding of a number of concepts in order to be able to design the simulations and then run the simulations and do the inference, etc. Right? Now those are the probability, the random numbers, the different sampling techniques, the probability distributions, this law of large numbers, why we need to do many number of experiments, and this virtual experiment or the simulation design itself, right? So we will be covering all these over the next in this playlist, but we'll start very basic. So I assume you are maybe even new to probability. So in the next few videos, we'll start with a coin or a dice, the 6-phase dice, and we will see how to compute the probability theoretically and then using the simulations. So we build up the concepts very slowly, and eventually we will work on problems like these with real world use cases. Okay. Thank you very much. In this video, we will learn the very basics of some probability concepts. Okay, we'll take very simple examples so that we know the all possible outcomes and we know the favorable outcomes so that we can compute the probability. Okay, exactly, right? So the probability definition is simply the number of favorable outcomes divided with the total number of possible outcomes. Okay, we will see examples. I mean, don't worry about too much about that definition, but this is the exact probability, right? So we work with very, very simple problems so that we know the exact value of the numerator and exact value of the denominator, right? In the later part of the videos, when we use the Monte Carlo simulations, we will not know. It is hard to know how many total outcomes will be there and how many favorable outcomes will be there. So that's why we do the simulations, and we compute the probability using the simulations. Okay. Now let's start with the most simplest example. We have one coin. Okay. Let's say we are flipping a coin, right? When we flip a coin, we either get head or tails. Okay. Either get heads or tails. So there are only two outcomes possible. Okay. Only two outcomes possible, right? So that's the number of total outcomes. Now let's say it's a fair coin, not tampered coin. What do I mean by that is both heads and tails are equally probable. Okay. We can have tampered coins where, for example, we can bias the coin to always have heads. Okay. Or to always have tails, right? So here we are not going to work with such examples. We are going to work with the fair experiments, right? Or the fair coin or a fair dice, etc. Okay. All right. Now the first question, what is the probability of heads? Okay. Now in this case, the favorable outcome is only heads, right? I mean, because this is the simplest example, it looks too trivial, but when we go to a bit more complex examples, it becomes clear why we need to explicitly state what are all the possible outcomes and what are all the favorable outcomes. Okay. So the number of favorable outcomes is only one. Okay. Then we compute the exact probability by dividing the number of favorable outcomes with the number of possible outcomes, right? Number of total possible outcomes. So in this case, it's 1 divided with 2. So we'll have 0.5. Okay. So this means when we flip a coin, there is 50% chance it can either be heads or it can either be tails. Okay. Both are equally probable. Then same story for a tails. Okay. So tails, again, we have the favorable outcomes, it's only tails, and the number of favorable outcomes is only 1. So the probability of tails is 0.5. Okay. Now let's say we are rolling a dice. Okay. You know, dice has 6 faces and we have numbers or the dots on each face, right? We can count the dots to get the number. So on 6 faces, let's say we have 6 numbers on this dice. Okay. So the total number of possible outcomes, that's 6 for a die. Okay. Again, we assume it's a fair die, meaning all numbers are equally probable. So the first question we are asking, what is the probability of getting 3 on the top face? Okay. So the favorable outcomes, it's only 3, right? Only 1. So the number of favorable outcomes is only 1, which is just this 3, right? So the probability of hits is again, it's 1 divided with 6. So that's about 0.16. Okay. So in every 6 rolls, we will get 1 with value 3 on its face. That's what this 0.16 means, right? Now it start get interesting. Now we are asking, what is the probability of getting an even number? Okay. So this time the favorable outcomes, right? So from the possible outcomes, what are all the even numbers? So number 2, number 4 and number 6, right? So the favorable outcomes are 2, 4 and 6. Okay. So this time we have the number of favorable outcomes 3. So the length of this list, let's say. Okay. So we have 3 favorable outcomes out of total 6 possible outcomes. Okay. So the probability again is the probability is 0.5. Okay. So now you start to see this favorable outcomes, right? Now let's say we are asking, what is the probability of number less than 5? Okay. Number less than 5. Now again, from our possible outcomes, which are these 6, how many numbers or which ones are less than 5? Okay, so we have 1, 2, 3, 4, right? So here we have our favorable outcomes 1, 2, 3, and 4. So the number of favorable outcomes is 4. That means our, sorry, this is not heads. I should have updated the text. But so the probability is 4 over 6, which is 2 over 3, 2/3, right? 0.67%. Let me just correct. So this is the probability. All right. So again, let me remove this thing. We have 3 more. Let me remove all these 3. Sorry about that. All right. Okay. So here we are. So the favorable outcomes are 1, 2, 3, 4 because we are asking a question, the probability for the number to be less than 5. Okay. So the number of favorable outcomes 4. So the probability is 4 over 6 or 2 in every 3. Okay. Now let's step up the game. Okay. So we have 2 coins this time. Okay. So let's say we have 2 coins. We are flipping the 2 coins simultaneously. Now the possible outcomes, right? So we can have both coins heads and heads, right? So the first coin is heads, second coin is heads. Or we can have the first coin heads and the second coin tails. Or the third possibility is the first coin is tail and the second coin heads, and finally fourth one tails and tails, right? So these are all the 4 possibilities. Now we cannot have other possibilities, right? So a coin can only have heads and tails, and when we flip 2 coins, it can be either heads and heads, or heads and tails, or tails and heads, or tails and tails, right? So we'll have 4 possible outcomes, right? So that's the total number of possible outcomes when we flip 2 coins. Okay. Now we are asking the question, what is the probability of at least one head? Okay, at least one heads. So from this one, if we look at least one head, so here we have 2 heads. Okay, that's a favorable outcome. Here we have an head, that's a favorable one. Here also we have a head, that's also favorable one. And this one, it's a tails and tails. So this is not a favorable outcome. Okay, so the favorable outcomes are heads and heads, heads and tails, tails and heads. So the number of favorable outcomes is 3. So the probability is 3/4. Okay, so 75%. That makes sense, right? When we are flipping at 2 coins, there is more chance to get at least one heads, right? All right. Now, let's say we are asking the probability of 2 heads. Okay, both coins should be heads. Again, we look at all possible outcomes. From this one, the favorable outcome is only heads and heads. Only heads and heads. This is only 1. Okay, this is 0.25. Now, if we compare these two, it is 3 times likely to get at least one head compared to 2 heads when we flip 2 coins. That makes sense, right? All right. Now we are asking probability of one head as well as one tail. So we want both head and a tail. Okay, both head and a tail. Okay, so again, going back here, this is not favorable, this is not favorable. So only we have these 2 as favorable, heads and tails and heads, right? Again, the probability is 2 over 4, that's 50%, right? And finally, we are asking the probability for 2 heads or 2 tails, right? 2 heads or 2 tails. So here we asked only for 2 heads, whereas here we asking these 2 coins can both be either heads or both be either tails. Okay. Again, we look at our search space are all possible outcomes. So head sign heads, tail sign tails. So that means we have again 50% probability. Okay. So as I mentioned, we are starting very basic. I'm assuming, I mean, this is for those who are new to probability. If you already know the probability, etc., you can skip the first few videos. Okay. It might be too boring for you. Now let's look at our final experiment, which is 2 dice, right? So this time we are rolling 2 dice. Now, as we know, each die can have 6 faces. Well, we'll have 6 faces, and each face has a number between 1 to 6, including 196, right? So the first dice, it can have 1, and the second dice can also have 1, right? Let's say the first die has 1. Now for the second die, we have 6 possible outcomes, right? It can be 2, 3, 4, 5, and 6. And similarly, when the first dice is 2, now the second dice, it can again have values between 1 to 6. So 6 outcomes, right? 6 likely values. So in total, when we roll 2 dice, we will have 36 possibilities like this. Okay, 36 possibilities like this. Now let's ask the question, what is the probability that both dice have the same number? Okay, so this time our possible outcome space, it has 36 values. Now let's look for the favorable outcomes for this particular question. And that question is having same number on both the dice, right? So here we have 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, and 6, 6. Those are the 6 favorable outcomes, right? So here we have the 6 favorable outcomes, and the number of outcomes, favorable outcomes, is 6. So the probability will be 6 divided with 36. So that's 1 over 6, right? So when we roll 2 dice, we will get the same value on both the dice 1 out of every 6 times, right? That's the probability. 1 out of every 6 times we get both dice the same value. All right. So let's look at one more. So here we have the probability of both dice having an even number. Okay. Again, we go back to all possible outcomes. So this time we are looking for both dice showing up even number, right? So if you look in this first row, the first die always has 1, right? So we can rule out this one, right? Because the first die is not even number. Now, if you look at this row, yes, the first die is always even number, but the second die sometimes can have odd number, right? So the favorable outcomes are 1, 2, 2, 2, 4, and 2, 6. So from the second row, we have 3 favorable outcomes. Okay, 2, 2, 2, 4, and 2, 6. And similarly, from the third row, we don't have any favorable outcomes because the first die is always odd number. And from the fourth row, we have 4, 2, 4, 4, 4, 6. Okay, we have 3 more, 4, 2, 4, 4, 4, 6. And fifth row will not have any favorable outcomes. And the final row will have 3 favorable outcomes, 6, 2, 6, 4, 6, 6, right? Right, this is 6, 2, 6, 4, 6, 6. All right, so the number of favorable outcomes is 9. The total number of possible outcomes is 36. So the probability is 1/4. Okay, and the final question, we are asking, what is the probability of one die having an even number and the second one having an odd number? Sorry, I made number of mistakes in this video. Odd number, and the total value should be greater than 9. Okay, so we are rolling 2 dice. One dice should show up even number, one dice should show up odd number, and the sum of the two numbers should be greater than 9. Okay, again, you can go through this. we can rule out all these values because some of them will be less than 9, right? So 6 plus 3 is 9, but we are looking for values greater than 9. So we can completely ignore the first 3 rows, right? And then if you look the bottom 3 rows, you will find these 4 satisfying the criteria, right? So the first criteria, at least one die should be even number, right? So if you look, there is one even number, 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 right? And the second criteria, there should be one odd number, okay? So here we have an odd number, odd number, odd number, and odd number, right? So these 2 criteria are satisfied. And then the third criteria, the sum of these numbers should be greater than 9. So okay, 6 plus 5, 3 plus 9 should be greater than 9. Okay, so this one goes. All right, 5, 6. Okay, these 2 will go. These 2 will also go. And then the number of favorable outcomes is just 2. So it's 2 over 36. That's 1 over 18. Okay, it's very, very low probability, 1 over 18. So 0.05. Okay, so it's very, very unlikely, or how many times? Only 5 times, 5 in 100 times we will have one dice as even number, the second one as odd number, and the sum of these 2 numbers will be greater than 9. Okay, so that's only 1 in 18 trials. Okay, it is too basic. I mean, I know it is too elementary, but as I was said, probability is confusing for a number of people. So I thought I'll explicitly state all these statements so that you can read and understand if probability is something which you find it hard. Okay. All right. That's it for today. Again, maybe very quick summary. When we compute the probability only for simple problems, it is possible to know the total number of outcomes and the number of favorable outcomes, right? Which is what we saw here. And the probability simply is the ratio of the number of favorable outcomes divided with the number of all possible outcomes. Okay. All right. Thank you very much. Hello friends. In this video, we will do our first, the very basic simulation, okay? Which is we are going to toss the coin multiple times and we'll see the probability for heads and tails, how the outcomes look like, etc. Okay. So in the previous video, we have learned that the exact probability is the ratio between the number of favorable outcomes to the number of total outcomes. Okay, that's the exact probability. Now, or the theoretical or analytical probability, right? The second way to compute the probability is simply repeat the experiment n number of times and count how many times we have the favorable outcome. Okay, so again divide these 2 numbers. Okay, now the reason this can be different from the exact probability is here we might not necessarily be computing the total number of outcomes, right? We might not necessarily have all favorable outcomes when we do the experiment, right? We can do, for example, imagine we have a problem where the total number of outcomes is 1 billion, okay? And the number of favorable outcomes is 1 million, okay? Now, we may not be able to do the experiment 1 billion times so that we can observe all the 1 million favorable outcomes, right? But even in that case, using Monte Carlo simulations and sampling techniques, etc., we still be able to compute the probability which will be very close to this exact probability. Okay, so that's why it is called observed probability, right? Right. Let's see an example. So here we are loading a bunch of Python libraries. We are going to mainly work with this random to generate some random numbers or samples, etc. And then matplotlib for plotting, and numpy maybe we may need to do some array manipulations. Okay. So again, we are asking this simple question: what is the probability of hits? Okay. So this is so simple problem. We know the exact solution, right? So we know exactly how many possible outcomes are there. What are the favorable outcomes, and the expected or the exact probability is simply the number of favorable outcomes divided with the number of possible outcomes. So in this case, it is 0.5. This is the exact probability. Okay. Now we are going to do some simulations. Okay. All right. So first we will flip the coin only once, right? So how many times we flip the coin, we are calling it number of trials. Okay. That's the number of trials. And Python has this very convenient function called random.choices. What we can do is we can provide a list of possibilities and it will return randomly. It will pick one of them. Okay, it will pick one of them and return to us. Now we can also provide a second variable called k. This is the number of trials. Okay, so first let me explain this function and then we will look at the rest of the code. So here the number of trials is 1. So this k value is equal to 1. So the possible outcomes is always going to be the same, right? Either it can be heads or tails. So when we run this function with k is equal to 1, it will return a list with only one element, right? So in this case, it happened to be heads. Okay. Now the same function here we are calling, but with the number of trials 2, meaning we are flipping the coin 2 times. Okay. So this time we happen to get one heads and one tails. So the first time we got heads and second time we flipped the coin, we got tails. Okay. Now let's say we are flipping the coin 3 times. Okay. So this time k is equal to 3. This means we should get 3 outcomes, right? So again, in this case, it happened that the first time we got head, second time we got heads, and third time also we got head. And finally, we have number of trials 4. This means we'll get 4 outcomes. Here are the 4 outcomes. They happen to be heads and heads, tails and tails for the 4 flips we have done, right? So we have this very convenient function where we can give the possibilities and how many times we want to sample. Okay. All right. So this is the outcomes. Here we are simply printing the outcome. So in this case, we flip the coin once and we happen to got heads. Okay. And we are asking the question, what is the probability of heads? Now the number of favorable outcomes, which is how many times we have heads in this list, right? So we have once heads. So the observed probability is the number of favorable outcomes, which is 1, and the number of trials, which is also 1. So the observed probability, we got 1. Hey, does this mean when we flip a coin, we always get heads? No, right? That's not correct. But why did it happen? When we say the probability of getting heads is equal to 0.5, what it means is if we repeat the experiment many number of times, half of the times we get heads, right? That does not mean we'll do the experiment only once and if we get heads, hey, my probability is 1. It is not, so 0.5 is not correct, right? It doesn't work that way. Or it can go the other way, right? When we flip coin only once, we might get tails, but that does not mean the probability of getting heads is 0, right? So that is why we need to repeat the experiment many number of times. That's what the probability also means. So the probability means when we do the experiment many number of times, what is the likelihood or what is the chance of getting that particular outcome, right? So that's why it is important to do the experiment many number of times. Okay. For example, okay, let's see here, right? Now let's do one more time. Okay, let me run this code. Right. So this time we still flip the coin only once, but this time we happen to get tails. So it's saying the probability is 0, right? So we can't do the experiment just once. But how many times do we need to do the experiment? We'll see that in a minute, okay? So this time we are doing the experiment 2 times, or we are flipping the coin 2 times, okay? So when we did it first time, we got 1 heads and 1 tails. So the number of favorable outcomes is 1 because we have 1 heads and the probability is 0.5. Hey, this is nice. So does that mean we need to do the experiment twice to get the probability correct? No. We'll see one more time. Okay, that looks good. Now see this time. We flip the coin 2 times, but this time we happen to get both time tails. Okay, we did not observe heads even once. So the number of favorable outcomes is 0, and that has led to the probability 0, right? This is also not correct. So that means even by flipping the coin 2 times, we cannot compute the probability of heads. Okay, so flipping the coin 2 times is not enough to measure the probability. Okay, so we should do the experiment enough number of times, or we should do enough flips so that the probability don't change or remain fairly constant, right? So let's do the experiment 3 times. Okay, now so when we did the experiment first time, when we flipped the coin 3 times the first time, we got head sign, head sign, heads. Now this again saying the favorable outcomes is 3, so the probability is 1. This is again not correct, right? So let's do one more time. So this time we got only 1 heads, so the probability is 1/3. Okay, one more time. Okay, we got 1/3. Now this time we happen to get all 3 heads. Again, the probability is saying 1.0, which is not correct, right? So 3 times is also not enough. Let's look at one more time before we do it many more times. Okay. So here we are doing we are flipping the coin 4 times. Okay. So for example, here we flipped it 4 times. We got 2 heads and 2 tails. So the number of favorable outcomes is this heads and this heads 2. So the observed probability is 0.5, which is a little better compared to flipping the coin only once. But this is also not sufficient. Okay. So see here, we flipped the coin 4 times. Now we got heads 3 times. That has led to the probability of 0.75 or 3/4, right? But we know the exact answer is 0.5, which is 1.5, right? Sorry. It's 1 in 2, okay, not 1.5. So even doing this experiment 4 times is not enough. Now let's use these loops from Python or any programming language. We'll do the flips many number of times, and we'll count the number of hits each time, and we'll compute the probability. Okay, so here we are going to flip the coin maximum for 100 times. Okay, so in experiment 1 we flip the coin only once, okay, and then compute the probability. In experiment 2 we flip the coin 2 times, we compute the probability. In experiment 100 we flip the coin 100 times and then compute the probability. Okay, so here we just defined this list, empty list. Okay, we are going to collect the measured probability for different number of flips. Okay, so here we are looping over this trials, right? So here we want to flip the coin up to 100 times. Okay, so first time we will be flipping the coin only once. Okay, so will be the number of trials. So this will start with 1 and it will go up to maximum trials. Okay. Okay, so here we have the outcomes, and from the outcomes we are counting how many hits we have, and that is our favorable outcomes. So we divide the favorable outcomes with the number of trials. Okay, then we'll get the observed probability. So this observed probability, we are simply storing it in a variable, in a list variable, so that we can later see how the observed probability changes with the number of trials. Okay. And here we are just printing some information, which is the number of trials, the number of favorable outcomes, and the probability. Okay. So when we run this with maximum number of trials 100, this is what we saw. Okay. So in a first experiment, we did only one trial and that happened to be hit. The probability is 1. Okay. In a second experiment, we flip the coin 2 times and both happen to be hits. So again, the probability is at 1. Right. In a third experiment, we flip the coin 3 times, but we got only one hit. The probability is 0.3. So as you can see here, this probability is fluctuating quite large depending on how many times we flip the coin, right? Now maybe here you start to see somewhere here the value getting close to maybe between 0.4 and 0.6, but it is still fluctuating quite a large, right? Between 0.4 to 0.6. And maybe here it is even just below 0.4. Okay. Now when we flip the coin 100 times, let's see what happened. So this time we flip the coin, let's say 99 times. Out of 99 times, we got hits 43 times. Okay, we got hit 43 times. So the probability is this of 0.43. Actually, this is a number of trials plus 1. So this is 100. Okay, number of trials. We are starting from 1. Okay, all right. So if we plot the number of trials versus the observed probability, this is how it looks like. Okay, so here we simply store the observed probability for each number of trials, right? So we are simply plotting the observed probability. Okay, so and then we are plotting a horizontal red line 0.5. This is the expected probability, right? The exact probability we computed before. So this is the expected probability, and the blue one is the observed probability. Okay. So as you can see, it's fluctuating quite large. So even when we did the experiment 100 times, the value is still fluctuating. Okay. Depending on how many the trials we did. Now let's do the experiment 1000 times, right? So basically we flip the coin 1000 times and we measured how many times we have hits, and that's this point. It looks better, but still, as we can see, maybe if the red line is 0.5, maybe this is 0.55, 0.45, let's say. So it is still fluctuating between 0.45 to 0.55. Okay. Now here we did the experiment 10,000 times. So for 10,000 flips, the distribution is getting narrower and narrower, as you can see here. So this is looking better. Now here we did the experiment 100,000 times. Okay, 100,000 times, and as you can see, the fluctuations have reduced very significantly. Okay, so the probability is getting, the observed probability is getting closer to the expected or the theoretical probability as we increase the number of trials. Okay, so that's the law of large numbers. Okay, that's why we need to do many number of experiments so that the observed probability can be as close as to the expected or the theoretical probability. Okay, that's all for today. Thank you very much. In this video, we will roll a 6-faced die and we'll ask a couple of probability related questions. Okay, so from the previous videos, we know that the exact probability is the number of favorable outcomes divided with the total number of outcomes. We know for simple problems, we can compute the exact or expected probability. But in this course, we are doing Monte Carlo simulations and we are doing some trials. These are called simulations or computational experiments. After doing the experiments, we are counting how many trials have led to favorable outcomes, and we divide that with the total number of trials we have conducted, and that will give us the observed probability. So in situations where computing the exact probability is difficult, we can perform the simulations and we can compute the probabilities. Okay. All right. So this is all the standard stuff. Now let's say we start with the question: when we roll a 6-faced unbiased dice, meaning all sides are equally probable, what is the probability that the number is greater than 4? Okay. So the possible outcomes are 6. Let's say that the dice is faced with these numbers 1 to 6. Now the favorable outcomes, there are 2, 5 and 6. So the expected or exact probability is the length of the favorable outcomes divided with the length of the total possible outcomes. So which is 1 over 3 or 0.33. Okay. Now here we have a helper function. We are going to roll the die multiple times and we pass the outcome to this function, and this simply count how many values are above 4, which is what we are looking for, right? So it will simply count the number of favorable outcomes and return that value. Now if we are asking what is the probability that the number is an even number, you can simply change the definition of the favorable outcomes. For example, here you divide with 2, and if the remainder is 0, then that would be a even outcomes. Okay, even numbers. All right. So let's start with just one trial. So here we are rolling the dice only once, and as we have seen in the previous videos, we are using this random choice function to which we are passing all the possible outcomes, and then we are sampling from this using this number of trials. So for example, when we pass this list, and if k is equal to 1, one of this number is picked up with equal probability for all 6. Okay, then we can say, okay, I want to roll the dice twice, meaning k is equal to 2. In that case, what we get is we get 2 numbers. Okay, so these 2 trials are independent of from one another. All right, so we roll the dice only once, which means we will get only one outcome. So let's say in this case we got the number 3. So then we are measuring the number of favorable outcomes, which is 0, because our favorable outcome is any number above 4, right? But we have got 3, so the number of favorable outcomes is 0. This means the observed probability is also 0. But we know this is not correct, right? I mean, when we roll a dice, surely we will get a number greater than 4, because it has 5 and 6 as well, right? But because here we have conducted the experiment only once, and we got number 3. So let's roll the dice one more time. I think I just repeated this, but let's say we are rolling the dice twice. So this function, it return a list with 2 values, right? So when we roll the dice first time, we got 4, and when we roll the dice second time, we got number 5. Okay, so the number of favorable outcomes is 1 because 5, and then the observed probability is 1 over 2, that's 0.5. Now if we repeat the experiment 3 times, in this case it happened that we got all 3 numbers below 4. So again the probability is comes out to be 0. So as you see, when we compute the probability using simulations or experiments, we need to repeat the experiment many number of times, so that we sample enough or all possible outcomes, then only we can compute the probability accurately. Okay, just one more trial before we do the trials many number of times. So here we are rolling the dice 4 times, and we happen to get 2, 4, 2 and 6, right? So the favorable outcomes only 1, which is this 6. So the probability is 1 divided with the total trials, which is 4. So we got it 0.25. But let's do the actual simulation, which is we repeat the experiment many number of times. right? So it's okay. So let's say we want to roll the dice a maximum of 100 times. Okay. So here we have defined this observed probability list, because for each time, so for in first experiment, we roll the dice once and we compute the probability. And in the second experiment, we are going to roll the dice twice and we again compute the probability. So that way we are doing 100 experiments. So in the 100th experiment, we roll the dice 100 times and we count how many favorable outcomes are there, and we divide that with the maximum trials, which is 100. That way we compute the probability with increasing the number of trials, right? So here we are just conducting the experiments from just 1 to maximum number of trials, and then using the random choice function, we are mimicking the rolling of dice, and this will return us the outcomes, and the outcomes we are passing it to this count favorable outcomes function, and then the observed probability would be the favorable outcomes divided with the number of trials, right? So this observed probability is for this particular number of trials, and then we store it in a list, right? And then here we are printing, for example, in experiment 1, we roll the dice only once. The favorable outcomes just happen to be 0 in this case, so the probability turns out to be 0. But as we increase the number of experiment, the probability slowly converges to the expected probability, which is 1/3 in our case, right? Which is 1/3, because we have 2 favorable outcomes out of 6 possible total outcomes. Okay, so as we increase the number of experiments, you see the numbers slowly start to converge to 1/3. Okay, now if we plot the observed probability with the number of trials, this is how it looks like. So as you can see at the very beginning, it fluctuates quite a lot, and this red horizontal line, that's the expected probability, which is 1/3. Now with increasing the number of trials, as you can see, this start to converge slowly to the expected probability. Okay, so here we did maximum 1000 trials, and here we did maximum 10,000 trials. As you can see here, we still see some small fluctuations, but the probability has converged to the expected or the theoretical probability. Okay, that's all for today. Thank you. In the previous 2 videos, we have simulated a coin and a dice, right? For these 2 simple systems, we know the total number of possible outcomes. For a coin, it's only 2 heads and tails, and for a dice, it's numbers between 1 to 6. So the total outcomes is only 6. Now in this video, we will get a sense of how the total number of possible outcomes grows exponentially, even for simple systems like coins and dice. Okay, so let's start with the coins. Now let's say we are flipping 2 coins simultaneously, right? So when we do this experiment once, we got a tails and heads, right? Now we want to find out the total possible outcomes and what they are, right? So here what we are doing is we are repeating this experiment some 100,000 times, and for each time we are flipping 2 coins and we are collecting the outcome, and we are checking if this outcome is seen before or not. So if this outcome is not seen before, then we are appending that outcome to this total possible outcomes. Okay, and finally here we are printing the total number of possible outcomes and what those outcomes are, right? For example, when we run this code, as you will see, it says when we flip 2 coins simultaneously, the total number of possible outcomes are 4, and those outcomes are both could be tails, both could be heads. The first one could be tails and the second one could be heads, and the other way, the first one could be heads and the second one could be tails, right? So when we flip 2 coins simultaneously, the total number of possible outcomes are 4. Okay, now let's flip 3 coins simultaneously. So here is one example, but now the total number of outcomes is 8, and these are those outcomes. Okay, now let's flip, for example, 5 coins. Now this time the total number of possible outcomes is 32, and these are all those outcomes. So each of these outcomes are unique, right? For example, one of these all heads, somewhere it should be there, and all tails, heads, and the remaining tails, so on and so forth, right? So if you observe the pattern, when we flip 2 coins, we got 4. For 3 coins, we got 8. For 4, we got 16. For 5, we got 32. So it is growing as 2 to the power of number of coins. Okay. So for example, if you are flipping 10 coins, the number of possible outcomes would be 2 to the power of 10. That would be 1024, right? So as you see, even for a coin which has only 2 possible outcomes, when we have multiple coins, the total possible outcomes is growing exponentially, right? It's growing as 2 to the power the number of coins. Okay, so now let's see how it grows for a dice, right? So for a dice, for each dice we have 6 possible outcomes, right? So let's mimic rolling 2 dice. Okay, so here is one example. We saw number 1 on the first dice, and in this case the second dice also showed up number 1, right? Now let's simulate this experiment 100,000 times. Okay, all right. So the total number of possible outcomes is 36, and as you can see, these are those 36 outcomes. So for example, I mean, here we can have, let's say, number 1 on first dice, and on the second dice we could have numbers from 1 to 6. So those are 6 outcomes. And then we have number 2 on the first die, and then on the second die numbers 1 to 6. So those are another 6, right? So this way we'll have 36 outcomes when we roll 2 dice. Okay, now let's roll 3 dice. We have 216 outcomes, and these are those outcomes. Okay, now let's do 5 dice finally. Now this is going to take a while. Now this number of trials is important. This number has to be much larger than the possible outcomes, right? For example, for 5 dice, we have 7,776 outcomes. Okay, this is how they look like. Now, had we conducted this experiment, let's say only 8,000 times, which is still more than the number of possible outcomes. Let me read it. Even if we do this experiment for 10,000 times, let's see. So it is saying the number of possible outcomes is just 5,000 plus, which is incorrect. The reason is we could have multiple trials producing the same output, right? So that's why here we are checking if this outcome is seen before. Only if it is not seen before, we are adding it to the possible outcomes. So that's why we need to run these experiments many times, more number of times compared to the potential outcomes. Then only all outcomes are sampled. Okay, so this is in a technical term, it's called this phase space. Now phase space has all these possibilities, and we are exploring this phase space. So we need to explore it more, then only we will be able to cover all the phase space, right? So similar to the coins, for the dice also, the possible outcomes is growing 6 to the power the number of dice, right? So when we have 5 dice, it is this 6 to the power 5, which is this 7,776, right? Now let's imagine we are rolling 10 dice at the same time, right? So the possible outcomes would be 6 to the power of 10. This is already 60 million. Okay, 60 million. Now we all know the Rubik's cube, right? So there are these 2 by 2 Rubik's cube, 3 by 3 by 3 Rubik's cube, etc. Right? So even for a simple Rubik's cube like 2 by 2 by 2, this has over 3 million combinations. It has over 3 million combinations. Now, even if you are able to produce one combination per second, and so 3600 seconds in an hour, and 24 hours in a day, it would take us 42 days just to reproduce the 3.6 million combinations of a 2 by 2 by 2 Rubik's cube. Okay, so such a simple system has over 3.6 million combinations. Now, if we take 3 by 3 by 3 cube, the number of unique combinations is this big, right? So it's this 43 quintillion. Okay, now it's this, the precise number is this 43 quintillion. Now again, let's say for each second we can reproduce one combination. So we are working, let's say 3600 seconds in an hour, and we are working 24 hours in a day and 365 days in an year. Even then, it would take these many years to reproduce all the unique combinations of a 3 by 3 by 3 Rubik's cube. Now, the age of the universe is 13.7 billion years. So if we divide with this, the age of the universe, it still be 100 times the age of the universe. So what it means is, in order to reproduce all the possible combinations of a 3 by 3 by 3 Rubik's cube, it would take us 100 times the age of the universe, even if we are able to reproduce one combination per second. Okay, so that's how these numbers or the possible outcomes goes, right? For example, in a real world scenario, let's say we have an outcome which is dependent on 10 variables. Now each variable can take hundreds of thousands of potential values, right? So then our output variable will have millions and billions of potential outcomes. So that's why we cannot reach all those variables, but using simulations, we can find out the most frequent ones, and from that we can infer the probability. So that's how the simulations are useful, even though we are unable to explore all possible outcomes. Okay. Okay, that's it for today. Friends, in the next few videos, we will solve some interesting problems using Monte Carlo simulations. Okay. So let's imagine we have a line segment of length 1 meter. Okay, so let's say for simplicity, let's assume it's lying along the x-axis. So the starting coordinate is 0 and its length is 1 meter. Now we are picking 2 points randomly on this line segment, and we make a cut at that points. So essentially we are dividing this line into 3 segments, right? For example, let's say we happen to pick up this point x1 and another point x2. So we cut this line into 3 segments, and then the length of each of these 3 segments is, let's say, s1, s2 and s3. Now the question is, can we form a triangle with these 3 segments? So what is the probability that we can form a triangle with these 3 segments? For example, in this case, let's say we roughly cut the line into 3 equal proportions, right? So using these 3 segments, yes, we can form a triangle, right? But let's take this scenario where the two segments happen to be very small and the third segment is very long. Now, can we form a triangle with these three line segments? The answer is no, right? So we want to simulate this system so that we can answer what is the probability that these three segments make a triangle. Okay. Now, all right. So again, we are going to do n number of experiments, large number of experiments or simulations, and the total number of favorable outcomes or the number of triangles is 0 to begin with. Okay. So we loop over the experiments, and then we are picking up two random numbers. So as you know, this will generate a random number between 0 to 1 with uniform distribution, right? So any number between 0 to 1 is equally probable. Okay, so we picked up two numbers, x1 and x2. Okay, and then what we want to do is, first we want to measure the length of these three segments, right? S1, S2, S3. So what we are doing is, let's say the point x2 happened to be larger than x1, something like this, right? X2 happened to be larger than x1. So what this means is 0 to x1 is going to be our first segment, x1 to x2 is going to be our second segment, and x2 to 1 is going to be our third segment. Now, if we want to measure the length 0 to x1, that would be x1. So the length of the first segment s1 would be equal to x1. Now the length of the second segment S2 would be x2 minus x1, because x2 is larger, right? So x2 minus x1, that would be the length of the second segment. And finally, the length of the third segment would be, here the endpoint is 1, so it's 1 minus x2, right? So this is the case when x2 is larger than x1. So here what we are doing is, if x2 is greater than x1, length of the first segment S1 is going to be x1, length of the second segment S2 is going to be x2 minus x1, x2 minus x1, and the length of the final segment S3 is going to be 1 minus x2, 1 minus x2, which is what we have here. Now, if it's the other way, for example, let's say x1 happened to be greater than x2, the logic simply reverses, right? So the length of the first segment x1 will be x2, because this is x2. Length of the second segment will be x1 minus x2, and finally the third segment will be 1 minus x1, because here we have x1. Okay, so far I guess up to this point is clear. All we are doing is, we have a line between 0 to 1, and we are picking two numbers randomly on this line. That means we have divided the line into three segments, and we are measuring the length of each segment. So with the help of this random function, we know it generates random numbers between 0 to 1 uniformly. So for each trial, we have generated two random numbers, and based on those two random numbers, we have measured the length of the three segments. Okay, up to this point clear. Now, we need to check if these three lengths or the segments can form a triangle. Now, for three lines to form a triangle, the condition is the sum of every two segments should be greater than the sum of the third segment. Okay, for example, S1 plus S3 should be larger than S2. Okay, similarly, S1 plus S2 should be larger than S3, and finally S2 plus S3 should be larger than S1. So which means the sum of any two segments must be larger than the remaining third segment. That's the criteria for three lines to form a triangle. Okay, so here what we are doing is, we are checking if S1 plus S2 is it greater than S3, and S1 plus S3 is it greater than S2, and finally S2 plus S3 is it greater than S1. So we are checking for every two sum of the two segments, is that larger than the third segment. Okay, if that's the case, that means we can form a triangle with those three segments. So we increase the number of triangles or the favorable outcomes by 1. Okay, and after this, Now we are just making some print statements. So the total number of trials or the number of experiments we have done, it's about 1 million experiments we have carried out. And then the number of favorable outcomes, it's roughly about 250,000-ish, 250,000-ish. So the probability of forming a triangle is 0.25, roughly 0.25 or 1/4. Okay. So you see how we can solve some interesting problems in maths also using Monte Carlo simulations. Okay. In the next few videos, we will solve some simple problems like these so that we can build the intuition, we get more practice. That's all for today. Thank you. There are a number of ways using which we can estimate the value of pi using Monte Carlo simulations. Today we will estimate the value of pi using one such method. Okay, let's assume we have a square. Okay, we have this square with side in some units 2, let's say 2 meters, right? So we have a square with side 2 meters. The origin is at the center of the square. So we have 1 and 1. So the square side is 2 meters. Now let's say we have a circle inside the square. So the circle edges touching the square edges at these 4 corners, right? So which means the radius of the circle is half of the length of the square, right? So the circle radius is equals to 1. The length of the square or the side is equals to 2 in some arbitrary units. Okay. Now we are going to drop some points from the top. So imagine this is on the ground. Let's say some rain is falling, or we are dropping some points from the top. Now first we ask the question, what is the probability that the raindrop lies within the circle? Okay. That's question number 1. And after we find that, we will see how we can estimate the value of pi using that probability. Okay. Again, to quickly summarize the problem, we have a square of side 2 meters. Then we have a circle inside the square of radius 1 meter. So we are dropping some raindrops from the top. Now they can fall anywhere within the square, right? Sometimes inside the circle, sometimes outside the circle, but still within the square. Now we are asking the question, what is the probability that the raindrop fall within the circle? After we find out answer to that question, then we will find out how we can estimate the value of pi. Okay. All right. So let's say we are going to drop some 100,000 raindrops. Okay, 100,000 raindrops are points. Now we want to generate 100,000 coordinates x and y, right? So 2 numbers for each point. We have x and y coordinates, and they should lie between -1 to +1. So both the x and y should lie between -1 to +1. Okay, so here we are using a uniform random number generator. So the value should be between -1 to +1, and number of such numbers is equals to the number of drops, which is let's say 100,000 in this case, right? So we have generated 100,000 x values and 100,000 y values, right? So the first value in x, the first value in y corresponds to a point on this plane within this square, right? So if you look at the first 10 values of the x, they look like this, right? So they are between -1 to +1 with equal probability. Now we know the coordinates, and now we want to find out if the coordinate or the point is within the circle or not. Now how do we find that? For example, let's take this point, right? So somewhere this point. Now if it lies within the circle, here is the origin. It's x square plus y squared. This distance should be less than the radius of the circle, right? If it is greater than the radius of the circle, that means the point is outside the circle. Okay. So what do we do is, for every point we have generated we compute x squared plus y squared, right? Because the origin is at the center. So x squared plus y squared gives us the distance of the point from the center of the square or the circle, right? So the center of the square and the center of the circle, they coincide, right? So x squared plus y squared give this distance. If it is greater than 1, that means the point lies outside the circle. If it is less than 1, the point lies inside the circle. Okay, so here what we did is we are checking if it lies inside the circle, meaning the distance is less than 1 or not, right? So is inside, this is going to be again a list of size same as the number of drops, but it will contain false and true like that, right? So true means that the point lies inside the circle. False means the point lies outside the circle. Okay, so here is inside, we are just computing how many truths are there by using a numpy sum. So this false is represented as 0 and true is represented as 1 when we do the sum. So all truths are counted and the number of points lying inside is roughly about 78,000. Okay, so if we measure the probability, so the total number of drops, we have done 100,000 drops, and among which 78,000 of them have fallen inside the circle. That means the probability of dropping inside the circle is roughly 78,000 divided with 100,000, which is 0.78. So the probability of dropping a point inside the circle is 0.78. Now, let's try to understand, let's try to build some intuition, right? Now, the probability of dropping inside the circle will be high if the circle area is high compared to the square area, right? For example, instead of having this big circle, let's imagine a small circle here, right? Then the probability would be low. Okay, so the probability is simply the ratio of the circle, the area of the circle divided with the area of the square. Okay, so for example, here the probability of the point dropping inside is equals to the area of the circle divided with the area of the square, right? So the bigger the area of the circle compared to the area of the square, the higher the probability. Okay, of course the circle area won't be greater than the square area because this is the maximum circle we can fit inside the square. Okay, all right. So in our case, we have so the circle area is pi r square. Pi, we have the radius 1, so it's 1 times 1, that's the area of the circle, and then area of the square is 2 times 2 because the side is 2 units, right? So this means the probability of dropping inside is equals to pi divided with the 4. Okay, which means pi value will be equal to 4 times the probability of dropping inside. Okay, so here we have the circle radius 1, the square side 2. Here we have computed the circle area and then the square area. All right, so the pi value is equals to 4 times the probability of inside. We have already computed the probability of inside, which is about 0.78. So if you multiply 4 with 0.78, we get this measured probability of our estimated probability 3.14, whereas the actual probability is also 3.14515. So these two are very close. Now, as we increase the number of points, I mean, in this case, we have done 100,000, but as we increase the number of points, this value gets even closer to the true value. Okay. Now let's do with very few points so that you can see how they are falling. So let's say we are dropping only 100 points. You see the 100 points, they are like here. It is even hard to see where the square and the circular shapes, right? As we increase more and more points, we have more points on the edge so that we can see where the circle stops. Okay, so let's increase the number of points, so maybe 10,000, which is 10 times less than the what we saw initially. So here we can see the circle. So out of those 10,000 points, roughly about 79,000 points, they have fallen inside the circle. The remaining 2,100 points, they are at these four edges. Okay, now the pi value is 3.16. Earlier we got 3.14, right? So as we increase the number of points, we get closer and closer to the actual pi value. So here we got 3.1139, which is close to 3.14. Okay, now here we are just plotting, we are just color coding the points which are inside the circle. So here what we did is x inside. So x contain all the, let's say, 100,000 points, and then we are filtering using the boolean, is it inside? So is inside has values true and false, right? So only when it is true, those values get copied into x inside and the corresponding y values. And here we just set the size because it is a square. We set equal dimensions in the x and y direction. Now here we are plotting all the 100,000 points. So if we disable this, that will be all the 100,000 points. And then those, and here we are plotting those points which fall inside the circle. So using this green color. Okay, so that's why we can clearly see the circle shape. That's all for today. As I said, there are many ways we can estimate pi using Monte Carlo simulations. Maybe we will look at a couple of different ways in the future videos. That's all for today. Thank you very much. In this video, we will solve another interesting problem called Buffon's needle. Okay, so it goes like this. Now imagine we have a plane or a paper with these horizontal lines, with these blue horizontal lines. Okay, please ignore these vertical gray lines. Those came as part of the plotting, but we'll have only these blue horizontal lines. Now let's say they are separated by one unit distance. Okay, so the distance between these two horizontal lines is 1 unit, and those are all equispaced. Okay, those are all equispaced. Now we have the needles of length, again 1 unit or 1 meter, right? The same as the distance between these two horizontal lines. Now similar to the raindrops or pi problem we solved in one of the previous videos, let's say from the top we are dropping these Buffon's needles. Okay, so the Buffon needle length is 1 unit. Also the distance between these two horizontal lines is also 1 unit. Okay, now when we drop these needles, they fell over this plane, right? Now some of them interact with these blue lines, like this one, like this one, this one, like this one, and some of them don't, right? Like this one, and this one. Now the task is to find out what is the probability that the needle will intersect with this one of the blue lines. Okay, it cannot do with the two lines because the length is exactly the same, unless it fall exactly in 90 degrees angle where it might touch both the horizontal lines, right? And from this probability, we can also compute the value of the pi. Okay, so let's see in this video how we set up this system and how we generate these needles, and hence we measure if they are intersecting with the lines, find the probability, and finally compute the value of pi. Okay, all right. Now, so simulating this plane is easy because all we have is just this imaginary horizontal lines separated by a distance of 1 unit, right? So these lines are at, let's say, 0, 1, 2, 3, 4, 5, 6, and so forth. Now we need to generate these Buffon needles, which means we need to generate two coordinates, right? One is this point, the other one is this point. So this point will have two coordinates xy, and this point will also have two coordinates xy. So essentially, we need to generate 4 points so that, but there is a constraint, right? The distance or the needle length should be 1 unit. Okay, so what we do is we generate 1 point or xy coordinates, x1 and y1. So we generate, let's say you take any one of these. Let's take, for example, this one, right? This blue one. So we generate x1 and y1. So this one end of the needle coordinate. And then instead of generating x2 and y2 with the constraint that the unit length should be equal to 1, what we do is we generate an angle, right? An angle between 0 to 3 degrees. So what we do is, let's say we have generated a coordinate x1 and y1. We generate an angle theta, and from trigonometry we know this forms a right hand triangle, and we already know the length of this needle, which is 1, or it could be any arbitrary L length, right? If the length of the needle is L, then the spacing between the horizontal lines should also be L. Okay, now from trigonometry we know the coordinate x2 will be equal to x1 plus the length of the needle, in this case 1, times the cos theta. Theta is this angle, right? Similarly, y2 coordinate will be y1 plus the length of the needle times sine theta. Theta is this angle. So what we do is we generate two coordinates x1 and y1. We generate the angle theta, and using these equations we compute x2 and y2. So this way we are already satisfying the constraint that the length of the needle should be equal to 1, right? So this is just a convenience to generate the second coordinates with that constraint 1. Now the tricky part is, okay, we have generated the needles, we place them on the plane. Now how do we find if the needle is actually interacting or intersecting with these horizontal lines? So what we do is, here are two scenarios, one where the needle is not intersecting, one where the needle is intersecting. So what we do is, so imagine these are our horizontal lines, we dropped a needle. So let's say the needle has fallen like this. Now what we do is, because the needles are along the y direction, whether the intersection happened or not is dependent purely on the y coordinate, not on the x coordinates, right? So what do we do is, first we take the minimum of y coordinates, right? For example, so this is 1 point, this is 1 point. So here we have y1, here we have y2. Now in this case, y1 is smaller than y2, but it need not be, right? For example, if the needle falls something like this, y1 will be higher than y2. Okay, so it doesn't matter which one is higher, which one is lower. But what we do is, we'll take the lower value of y, which let's say in this case happen to be, let's say some 0.3, right? So if this is 0, this is 1, let's say 0.3. Now we apply seal, which means we are rounding it up to its nearest integer, right, on the higher side. So essentially we have converted this y1 equal to 1 in this case, right? And similarly for the larger coordinate, which is in this case y2, we apply the floor. Okay, the instructions are here, you can read through. So we have converted this y2 to 0. So in such a case, the needle does not interact with any of the lines, right? Whereas in a scenario like this, here again we have y1 smaller, y2 larger. So we apply seal to y1, which means this coordinate we transformed it to 1, or we computed a new value which is equal to 1, and to y2 we have applied the floor, so the value has become 1. So if the result from step number 2 and step number 3, which is applying the floor and seal functions, if these two happen to be equal, that means the line or the needle intersect with the one of the horizontal lines. So that's how we are going to find out if the line intersect, if the needle intersect with the horizontal lines or not. Okay, so let's see how we generate. All right. First we generate only 100 needles. This is for demonstration purpose, but this will not, as you know, this will not give the right probability, because if we generated, let's say 100,000 or a million needles, we wouldn't be able to see this image this clearly, right? So that's why first I ran this experiment only with 100 needles. Okay, and here we have the number of hits. To begin with, it is 0. Now we are going to generate lots of needles, right? 100 needles, which means each needle will have 4 coordinates. That would be x1, x2, y1, y2, or here I call them xi, xj, yi, yj. Okay, so for each needle, we are going to have the 4 values stored in these variables, so that at the end of the experiment, we can plot the needles here. All right. Okay, so let's generate the needles. Now, let's say our plane start from 0, in the y coordinate start from 0 and all the way up to 11, right? So we want to generate the y coordinates between 0 to 11. Now in the horizontal direction, it doesn't matter, but just to make it square-like, we will do the same dimensions. Now in the horizontal lines, it can be as long as you want. It can be 100,000. It doesn't matter, right? Only in the vertical direction, we have this constraint that the plane or the paper is from 0 to 11. So what we do here is, so here we are generating one coordinate for x1, okay, which will be between 1 to 11, and then this will be 0, so this will be 1, and then similarly we are generating this y coordinate using the same similar method, right? After that, here we have generated the angle. We have simulated this angle, so we generated 2 coordinates x1 and y1, and then we are picking up an angle theta, right? That's also we are generating randomly. Okay, so this angle will goes between 0 to 2 pi, right? Because we know this n pi rand function, it will generate a random number uniformly between 0 to 1, right? So here we have generated a theta between 0 to 360 degrees. Now our x2 and y2 coordinates are simply be x1 plus the length, in this case happen to be 1, so x1 plus cos theta. Our y2 will be y1 plus sine theta. Okay, so y2 will be y1 plus sine theta. So here, by this time, we have generated one needle. So we have generated a x1, y1, we have generated a theta. Using these 3 values, we have computed the x2, y2 values, which means we have generated one needle. Okay, so with this code, we have generated one needle. Now we are checking if the needle intersect with one of the lines. Now, as we discussed before, it's very easy. All we do is, using the y coordinates of the needle, first we will find out the minimum value of y, and then we apply the ceil function to the and to the max y value we apply the floor function. Now the result of these 2 transformations is not the same. That means the line don't interact, or the needle don't interact with the lines. If the result of these 2 happen to be the same, which is in this case, then that means the needle intersect with the lines. So all we are doing is, first we are finding out the minimum of y1 and y2. Okay, the minimum of y1 and y2, and then to the minimum we are applying the ceil. Okay, to the maximum we are applying the floor. Okay, so to the minimum we are applying the ceil, to the maximum we are applying the floor. Similarly here, to the minimum we are applying the ceil, to the maximum we are applying the floor. Now the result of, if these 2 operations is equal, then that means the needle is intersecting with the lines, otherwise not. Okay, so here we are checking. Now if the result is the same, that means it's interacting, which that's a hit, right? So here we are increasing the hit by 1. So the check will have a value of either 0 or 1. If these two are equal, then it will be 1. If these two are not equal, this will be 0. So if they are equal, that means the needle intersect with the lines, and that means we are increasing the number of hits by 1. Okay, and finally we are saving the needle coordinates in these lists so that we can plot them at the end. All right, and finally the probability of the needle intersecting with the lines is simply how many lines or the needles have interacted with the lines divided with the how many needles we have dropped, right? So for this small experiment, we dropped a total of 100 needles, and then the number of needles intersected is 56, which means the probability of intersection is 0.56. But again, as you know, this number is too small to say this is the right probability. But now mathematically, this probability will be equal to it's 2 times pi, which means the pi value will be the probability will be 2 divided with the pi. Okay, again we are not going into the mathematical derivation of this problem, but the probability will be equal to 2 divided with the pi, which means if we reorganize the variables, pi value will be equal to 2 divided with the probability. So 2 divided with 0.56, we have got a value of 3.57. But let's do one thing. Let's increase the number of needles, and let's recompute the probability. Okay, let's rerun this. Yeah, as you can see this time, this is the probability of intersection, and the pi value is also very close. So it's 3.14, right? The actual pi value. Now it's this one. Let's increase one more digit. This simulation might take a bit long, but let's do this. All right, 3.149. So here we are getting very close, 3.14 to the actual pi value. And here all we are doing is simply we are just making this grid, these horizontal lines, and we are plotting the x and y values. Here we, for the plot layout, we choose a square layout so that we can see it clearly. Okay. All right, that's it for this video. Thank you very much. In this video, we will solve an interesting problem called Monte Hall problem. It's actually a game, and the game goes like this. So there are 3 doors in this game, and behind one door there will be a car, and behind the remaining 2 doors there will be goats. Okay, and you are asked to pick one of the doors. Once you pick the door, the host will open a door which contain a goat, and then ask you if you would like to make another choice. Okay, for example, let's say in this picture this 3rd door is closed, but just imagine we have these 3 doors closed, and for simplicity let's just assume behind door 1 there is a car, behind door 2 and 3 there is a goat. Okay, now you are asked to, in step number 1, you are asked to pick a door, right? So let's say you have picked door number 2. Okay, and in step number 2, the host, who already knows which door contain the goats, which door contain the car, he will open one of the doors. Since you pick door number 2, which has a goat, the host will have only 2 options to choose, right? 1 or 3. Because he already knew that behind 1 there is a car, what he do is he or she open door number 3 to disclose there is a goat behind, right? Then he will ask you, hey, do you want to stick with your initial initial selection number 2, or do you want to switch to door number 1, right? Now, in this problem, we will ask, what is the probability of winning this game, meaning winning a car, if you do not switch, right? And what is the probability if you switch? Okay. Now, let's see how the game goes, and then we will solve it using Monte Carlo simulations. Okay. First, again, let's assume we have car behind door number 1. We have 2 goats behind door number 3 and door number 2 and 3. Okay. Now, here we are doing 10 experiments, and in the first case, let's say you are not switching, right? So you are sticking to your initial guess. Okay. So initially, let's say you have picked door number 1. Okay. Because door number 1 has a car, the host, he will either open door number 2 or 3 and then say, hey, do you want to pick the remaining one, right? So what the host did is he picked door number 3 and he asked you, hey, do you want to stick with door number 1 or do you want to switch to door number 2? Because in this case, we are not switching. You stick to your initial guess, which is door number 1, right? So your initial guess and final option are the same, because you are not switching based on what the host has done, right? So for example, in second experiment, your initial selection is door number 3, and the host opened door number 2 and he asked, hey, do you want to stick with your initial option 3 or do you want to switch to the remaining option 1? You stick with your initial option, which is number 3. Okay, so it goes like this, right? So these are the initial options, and then the host picked one of the doors which has a goat behind. He asked you to switch if you would like to switch, but you did not switch. So your final option also the same as your initial option. Okay. Now we'll come to the winning probability, etc. Here we have done only 10 simulations. By now you are already familiar why we need to conduct many number of experiments to get a right estimate of the probability, right? Now, this is the second scenario. Let's say you are switching, right? For example, your initial guess is 1. The host has opened the door 2, which has a goat, and he asks you, hey, do you want to switch to door number 3 or do you want to stick with your initial option, door number 1, right? Because in this case, you are switching. So you are switching to door number 3, right? For example, here, in the second experiment, the same thing happened, but in the third experiment, initially you chose door 2, host opened door 3. That means you have switched to door number 1, right? So this is your final option, right? So after host has opened a door, he gave you the option either to remain with your initial selection or to switch to the only remaining door. Okay, so the game goes like that. Okay, I hope this how it goes is clear to you, right? Now let's simulate this process. Now, so we have 3 doors, 1, 2, and 3. Now let's put car behind one of these doors and goats behind the remaining 2 doors randomly, right? So here I'm making a random choice on these 3 doors. So I'm picking just one door. In this case, it happened to be door number 1, right? So behind door number 1, we are putting a car. And then the remaining 2 doors should have the goats, right? So here I'm just using this set function from Python. So we cannot subtract list from list in Python. I mean, removing the common elements, right? Not the element by element subtraction. So what I have done is, so the doors, this has 1, 2, 3, and the car door, which is this one. So with this set operation, we are finding the remaining 2 doors, and then we are converting it back to list. So the goats are behind door number 2 and 3. So with this code, all we did is we have 3 doors, and we selected one of the doors for car and the remaining 2 doors for the goods, right? Now let's conduct the experiment. So we are writing a function here. Now we are going to run this experiment n number of times, and we give the user the option to switch or not. Okay, so we run this experiment first time with the user not switching, and second time with the user switching, and then we compute the probability without switching and with switching to find out which one is the best option to. Okay, now again, let's spend a bit more time on understanding this problem, right? So initially, the probability of winning this game is 1/3, right? Because we have total 3, and each one has equal probability, right? And the car is behind only one of the doors. So which means the probability of winning this game is 1/3, right? This is if you do not switch after the host has offered you to switch, right? Now, let's say the host has offered you. What is the probability if you switch? A probability of winning if you switch the door, right? Now, even though it's a simple problem, most people think the probability would not change because each door has 1/3 of winning probability. So whether the host has opened the door and give you the option or not, the probability of winning remain the same. So most people think whether you switch it or not, right? And some people think, okay, since one of the door is eliminated, now the car is behind one of these, let's say one of these doors, so the probability of winning now increased to 0.5. So increased from 0.33, which is 1/3, to 0.5, because now we have only 2 options, and the door and the car is behind one of these 2 doors, right? So both answers are incorrect, as you will see. Switching the door will actually increase the winning probability by another 1/3. So if you stick with your option, initial option, there is only 1/3 winning probability, and that's easy to understand, right? But had you switched, your probability of winning this game will be 2/3 as opposed to 1/3. Okay, it's a bit tricky to understand. There are lots of Wikipedia and other blogs where they explain this process very clearly. So you might want to read this, right? But today we will just simply solve this problem using Monte Carlo simulations. Okay, now I'll explain why the probability increased to 2/3. Okay, so let's say we are switching here, right? So we have made an option 2. So our initial options have 1/3 winning probability. Now, which means our probability of losing is 2/3. Okay, our probability of winning is 1/3, and our probability of losing is 2/3. Now the host has eliminated one of the doors, which means the remaining door has a probability of winning 2/3, right? So initially each door has 1/3 probability. Now the host has eliminated one of the doors, so that probability will be switched to, these 2 doors have 2/3 probability, right? The door which we have not selected. Now the host has eliminated one of the doors because he already know there is a goat behind, which means the other door will have a winning probability of 2/3. It's a bit tricky, but go to the Wikipedia page and read it. There are different ways of explaining it, and you will understand. Okay. Okay, so let's start the simulation. So we are going to run the simulation n number of times with a switch or without switch option. Okay, all right. So do the experiment. This is a function call. Here we are doing the experiment n number of times. And the first time, for example, we have made an initial selection. Now, after we made an initial selection, which is simply picking one of the three numbers. And then the host will make a selection, right? But at this point, what are the host options? I mean, when we begin, we have three options to choose from, and we pick one of the options. Now, the host will have only either two or one option to open the door. I'll tell you. So, for example, in this case, let's say the car is behind door 1 and the goats are behind door number 2 and 3. Now, let's say you already picked, you happen to pick door number 1. So, then the host from 2 or 3, from 2 and 3, the host will pick one of the doors, right? So he might open door number 3 or door number 2 or door number 3. Now, what if you have picked door number 2 as your initial option, right? If you pick door number 2 as your initial option, because the host already knew that the car is behind door number 1, the only thing he could do is he opened door number 3 to disclose you the goat, and then he will ask, hey, do you want to stick with your initial guess of door number 2 or do you want to switch it to door number 1, right? So that's what we are doing here. So from all the doors, here we are removing the initial selection, okay? And then the host will have the two options. So the host will have the two options from the goat doors, right? So from the goat doors, we are removing our initial option. Now our initial option might be one of the goat doors or not. So if it is one of the goat doors, then the host will have only one door to open. But had we selected a car door at the beginning, then the host will have two doors to open and he will pick one of the doors, okay? And from the host options, he will make a selection, right? So the host has made a selection. Now, after making the selection, the host will ask you, hey, do you want to switch or not? Now, let's say you are not switching, okay? If you are not switching, then your final selection is same as your initial selection, okay? Your final selection is same as your initial selection. So if we are not switching, the problem is very simple. So from the three options, you select an option. What the host does here does not matter because we are not changing our decision. So your final selection is simply your initial selection, okay? But let's say you decided to switch. So you are switching here. Now your final selection will be from all the doors which are there. Initially the three doors are there. You have made an initial selection. Host also made a selection, and now you have to make a selection which is not either of these, right? So out of these three, you are eliminating here we are eliminating two options. That means we left with only one door, right? So that's going to be our final selection. So for example, to explain this, what we did is, so let's say our initial selection is 1, the host has selected 2, and then the host gave you the option, hey, do you want to switch or not? Now our initial option is 1, so we are not remaining with that, and the host already disclosed there is a goat behind 2, which means there is only one option left, right? So our one option and final option is door number 3. Similarly, let's take this. So initially we have selected door number 3. The host opened door number 2 to disclose the goat, and then that means we are making a selection. So we cannot, we have to switch from 3. We cannot choose 2, which means the only option we have is door number 1. So that's what we are doing here, okay? And then here we are printing what we just saw here. So what is our initial selection? What has the host selected? And what is our final selection? Now, if our final selection is equal to the car door, then we win the game, right? So we run this experiment many number of times, and here we measure how many times we win the game. And finally, the probability of winning the game is number of wins divided with the number of runs, okay? So initially, we run this experiment just 10 times so that we can see all this output, right? So what it would look like if we do not make a switch, and what it would look like if we make a switch. But these probabilities are incorrect because we have run the experiment only 10 times. Now let me disable this line and let me run the experiment many number of times. Okay, so here what we are doing is our switch option is no, so we are not going to switch, and we are doing the simulation here for n number of runs with the switch option no. And then this function returns the probability of winning. So here we are printing the probability of winning, right? That's the first set of experiment. And this time we have decided to switch. So switch is equal to yes, and we are doing the same experiment. But this time we have decided to switch when the host asks us. Now again we are computing the probability, the function will return, and we are printing it. Okay, so let me run it. Oh, sorry. So let me run this function. Now we'll see. Okay, so if we stick with our initial option, as you know, it's a straightforward problem. The probability of winning is 1/3 because there are 3 doors and the car is likely to be behind any one of the 3 doors. So the probability of winning is 1/3 if we don't make a switch. But if we make a switch after the host gave us a second option, our probability of winning has increased to 2/3, right? From 1/3, it has increased to 2/3. This is a quite tricky yet very simple problem. As I said again, maybe if you want to think through, go to the Wikipedia page, and there are a number of blogs which explain this very clearly. Right. So to summarize, by switching the door, our chances of winning the game have doubled. Okay. That's all for today. Thank you very much. In this video, we will simulate a casino-like betting game. It's a very simplified version. I thought of simulating the roulette game. Because of the so many rules, the code and the video will becomes too long. So I choose a very simple game. Okay, it's a spinning game. So it looks like this. It has these 3 divisions: yellow, red, and blue. And you bet on one of the colors. Okay, so let's say you bet on yellow, and if the arrow lands on yellow, you gain $1 or 1 point. And similarly, if you bet on blue, and if it lands on blue, you will gain 2 points. And red is where you lose points or money. If it lands on red, you will lose 3 points. So if you bet on yellow or blue, but if it lands on red, you will lose 3 points. Okay. Now, let's say each game consists of 10 rounds. So which means if you are playing one game, that means you are actually playing 10 rounds. Okay. So we will simulate this game for 1 million times, and we will ask a number of probability related questions. Now, by now you are already familiar with Monte Carlo simulations, etc. Here, the important thing is, how do we frame this problem? I mean, how do we translate this game into this random numbers sampling thing, right? For example, here we are saying if it lands on the yellow region, you will gain 1 point, right? So the yellow region consists of 50% of this circle, right? So the arrow lands on one of these regions. These 3 regions consists of 100%, and yellow consists of 50%. So what do? Is we simulate a random number between, let's say, 0 to 1 or 0 to 100. It doesn't matter, between a fixed width. And then let's assume for simplicity it's between 0 to 1. If the random number happened to be between 0 to 0.5, then we say the arrow has landed on yellow region. Or you can say it is between 0.5 to 1.0. So it is up to us. So as long as we take that 50% of the random number range, that would be the yellow region, right? So for example, here what we are doing is we are defining a function. We are going to, for each game, and each game consists of 10 rounds, right? So that's why we are looping over 10 values. Now we generated a random number. Now we know this value is going to be between 0 to 1. So here what we are doing is, if the value is below 0.5, we are calling that yellow region, and our number of points will increase by 1. So let's say we begin with 0 points, but let's say we are allowed to play this game as long as we want, even if we are with negative balance. Okay. Or you can frame this as, if R value is greater than 0.5, then also you can call it a yellow region. Okay. And then let's look at the blue region. So this consists of 25% of the circle area, right? Then we can say, if the random number is greater than 0.5 and less than 0.75, that we can call blue region. Or we can say, if the random number is greater than 0.75, which means 0.75 to 1.0, which is about 20, which is exactly 25%, right? So we can either frame this as R greater than 0.5 and less than 0.75, or R greater than, or the random number greater than 0.75. So that would be blue region. So our points will increase by 2 points, right? And finally, the remaining region, which in this case would be greater than 0.75. That's what remaining, right? So up to 0.5, it's gone. Between 0.25 to 0.75, that's also gone. So the remaining region, if R is greater than greater than or equal to 0.75, that would be this red region, and we lose 3 points. Okay. So the tricky part, as I was saying, is, I mean, this is still a very simplified problem. In the upcoming videos, we will see a bit more trickier and realistic problems. But translating this into these random numbers samplings is the real tricky thing. Okay. And then after playing one game, which consists of 10 rounds, it will return the number of points. Okay. So let's define these points as a list. We are going to play this game 1 million times, and each time 10 rounds. And after the 10 rounds, we are counting how many points we have. So we have started with 0, and here, so we call the function, meaning we are playing the game, and then this function returns the number of points after the game or the 10 rounds, and we have collected the points into a list, right? So this is how it looks like. Now the length of the points is going to be 1 million, because we have played the game 1 million times. Now if you look at the first 10 elements, this is how they are, which means in the first game, after 10 rounds, we have gained 4 points. In the second game, again after 10 rounds, we have gained 10 points. Whereas in the third game, we actually lost, right? So we begin with 0, but by the end of the game, after those 10 rounds, we have lost 10 points or $10, right? Now we'll ask a number of probability related questions. Okay. And we can answer all those questions just by using this points list, right? Which is of length 1 million. So let's start with a simple question. What is the probability that we will make a profit by playing this game, right? And the game consists of 10 rounds. Okay. So all we need to do is, we go over all the values in this points list, and we'll check how many of them are greater than 0, right? We are looking for profit. So the points or the p-value should be greater than 0. Now this logic will return a boolean, true or false. Now when we compute the sum, all truths are considered as 1. So this will return the number of times the values in this list are greater than 0. Okay, that means we are making a profit in those games. So the probability is the number of times we made the profit and the total number of games we have played. Okay, so this just rounding the probability to 3 decimal points. Now then finally, if we are printing the probability of making a profit by playing this game. Okay, so it's 0.63. All right, and then let's reverse this question. What is the probability of making a loss, right? So all we need to do is check or the count the number of values which are less than 0. So which are less than 0. So only this thing is changing. So the probability of making a loss is close to 0.28, right? 0.29, let's say. Now, it could be that we profit or loss. So let's look at that probability as well. So the sum of these three probabilities should be equal to 1 because there are only 3 possibilities. So it's 0.63, 0.93. Yeah, that's right. That's right. Okay. So 0.63 plus 0.28 plus 0.07, that would be equal to 1. Now we have some rounding of error because we are rounding the values to just 3 decimal points. So to answer this question, we just need to check how many times we have 0 as the points, right? So we begin with 0 and we are checking how many times the p-value or the points value is equal to 0. So that probability is about close to 0.07. Okay, and then let's ask more questions like, what is the probability of making a profit greater than x? Okay, so again, very simple logic. So let's say here we want to compute the probability of making a profit, let's say greater than 0, greater than 1, greater than 2, so on and so forth, up to let's say 20. So in the final question, here we are asking a number of questions. What is the probability of making a profit of greater than $20 or points? Okay, so we are looping, and for each time we are counting how many times the profit is greater than the reference value. Okay, a very similar thing. So here it says the probability of making a profit of making any profit, right? Greater than 0 means it could be 1, it could be 2, it could be 10, anything, is 0.634, which should be equal to this value, right? This is the probability of making a profit. Now, as you can see, with this value increasing, obviously the probability will decreases, right? And this says we cannot make a probable profit of more than 17 points. Okay, so 16 is the maximum. So by playing this game 10 rounds, even if it lands on this, let's say the blue every time, the probability of making a profit, I mean, I guess if it lands on the blue every time, we will make a profit of 20, right? We will make a profit of 20, but that probability is so small that when we did the rounding, it became 0. Or maybe let's remove this rounding thing. We might need to simulate more times so that also happens. Yeah, here we can see, right? This is extremely small. So when we played the game 1 million times, we have played the game 1 million times. In those 1 million times, only one time we have made a profit of 19. So the probability of making a profit greater than 19 is just 1 in a million, right? So again, as this number increases, the probability decreases, and it seems like the most likely profit we will make is somewhere around 2 or 3, something like that, right? So in this region, the probability is still greater than 50%. Okay, and similarly, we can ask what is the probability of making a loss greater than some value, right? So all we are doing is we just reverse this. and we are checking how many times the value is less than this reference value, right? So again, it says it's impossible to make a loss of greater than 20 points, right? So even if we uh, uh, right, and the most likely loss we make, it's somewhere around some 2, 3, or 4 points, right? So in this region, these are the high values, right? And finally, we can ask the probability of making some exact profit, right? So here we have asked the probability of making a profit greater than a specific value, right? Whereas here we are asking the probability of making an exact profit of 1 point, 2 point, 3 points, etc. So obviously these values will be smaller, because here when we ask this question, this probability includes all these values as well, right? So that whereas here it's the exact value. So that's how it goes. All right, that's all I want to say. As I mentioned, roulette game should have been much more interesting, but it has too many rules, so the code will become too lengthier in the video also. But you understand how we translate the game into these random numbers, right? By generating and sampling these random numbers, we can simulate any betting game we see in casino. Okay, and we can compute the probability of us winning versus the host winning, etc. Okay, that's all for today. Thank you. We will simulate an interesting problem called random walk. In a 2 dimension, it goes like this. Let's say we have a person here, and the person is drunk, so he don't know where he is going, where he came from. Okay, so he don't have any memory. The person do not have any memory, and the person at each step he can either go in the up direction or down direction or left or right, and these 4 are equally probable. As I mentioned, the person do not have any history. For example, if the person has made 5 moves all in the right direction previously, that does not uh, stop him from making another move in the right direction, right? So the what the person did in the past has no influence on the future. Okay, the person has no memory, no history. Okay, and this is a 2 dimension version of the problem. We have 1 dimension one, 3 dimension one, and the step length, it don't have to be fixed, it can be continuous as well. Okay, now this process is called Markov chain. It has mainly the properties which I described, like it has no memory, and what it does next is not influenced by what happened in the past. Okay, now this might look like uh, a pointless problem, but it has many applications in science, engineering, finance, biology, etc. In almost every field, random walk has some sort of applications. For example, in sciences, random walk is used to study how how the molecules move in gases and liquids. In finance, these models are used to study how the stock price varies with the time. Okay, and also in computer science, the random walks are used to measure the size of the web. Uh, uh, in health sciences, they can be used to study the uh, spread of the disease. Okay, so coming to this video, we will simulate a 2 dimension random walk. For simplicity, we start somebody starting at origin. For example, this is origin, so the person will start from here, and will make the person take some n number of steps, and each step the person will choose one of the directions randomly, all equal probability, and make a move, right? And then again make one more move independent of what happened in the previous step, and it goes on like that, right? So we'll simulate this process and we'll see how the output look like. Now we are not going to ask any probability question. There are we can ask many number of questions, but we will just simulate the walk, and we'll see what sort of questions we can ask at the end. Okay, let's look at the code now. Here we have a new library which we have not used before. So matplotlib, it has this function animation method using which we can create animations. So when we do the plotting, we can create them as animations, which we will see in a minute. Okay. Now this has we have seen this before from IPython display. We can have display, HTML, etc., etc. Right? So let's write a function to simulate the process. Okay. So the function simply takes how many number of steps, and we are assuming the person always start at the coordinate 0, 0. Okay. And here we are looping n number of steps, right? And these ones, X list and Y list, we are going to track the person movement so that we can visualize at the end of the simulation, right? Now, as we were discussing, the person has 4 choices, right? Whether we can call it up, right, down, left, or we can call it north, east, south, west, etc., right? So by using the random choice function, at every step, we are picking one of these directions with equal probability. Okay, with equal probability. That's important. And then let's assume the step length is also 1. Okay, so if the chosen direction happen to be, let's say, north, that means the person is going in the up direction, right? So only the y coordinate will change. So from the current position, we update the y coordinate by 1. The x coordinate remain the same, right? So as you saw here, when a person start from here, let's say if you go in the up direction, only the y coordinate changes. The x coordinate remain the same. Similarly, if he goes to the bottom, again the y coordinate changes by -1, whereas the x coordinate will still remain the same. And similarly, x coordinate will change if the person move either left or right, right? And then y coordinate does not change. Okay. So if the chosen step is north or up, we are increasing y coordinate by 1. And in the opposite direction, if the chosen step is south, which is down, we are reducing the y coordinate by 1. So delta or the step length is 1 here, right? And similarly, if it's east, which is right, so the person is moved at that point to the right, so the x coordinate increased by 1. And the fourth option, if it's to the left, x coordinate reduces by 1. Okay, so for every step, we have computed the updated coordinates, right? And then these updated coordinates at time, let's say t+1, we have stored them in this list. And finally, we are returning these 2 lists, XL and YL, right? So if the person has taken 100 steps, which means these 2 lists each will contain 100 values. Okay. Now, this is one way to simulate the process. And let's look at another process. Because this is so simple, there are many number of ways we can do it, right? So this part is same. Again, the person starting from x and y 0, 0. These ones to keep track of the movement. And again, we are simulating for n step. So this time, instead of randomly selecting a string and updating the coordinates, here we are having the delta, I mean the delta x and delta y's, right? For example, the person might move right. If he is moving in the right direction, up direction, the x coordinate will remain the same, the y coordinate will increase by 1, right? So this represent moving in the up direction, whereas this represent moving in the down direction, because there is no change in the x coordinate. A y coordinate changes by -1, right? This means it's the movement in the down direction. Whereas this one, it's x is equal to 1, which means the person is moving in the right direction, and y coordinate does not change. And finally, this one, it's a movement in the left direction. That's why it is -1, and no movement in the y direction, right? So instead of randomly selecting a direction and then making the delta or the update, here we are doing both simultaneously, right? So here we are directly sampling the movement, and then we simply update both x and y coordinates. So for each step, again, As you can see in all these 4 options, there is 1 0, right? So either X coordinate or Y coordinate gets updated. And we are finally updating the list to keep track of. So first let's simulate this for just 100 steps. Okay. Now we call the function. Now either we can call this random walk 2 or random walk. Both will give same results, right? And then we have these 2 lists. Now let's plot these lists to see how the person has moved. Okay. Now the final coordinate will be the last element in this X list and Y list, right? So that would be, I mean, in this case, it happened to be -3, -7. So the person has started at 0, 0. So which is this coordinate. He has started at 0, 0 and then ended up at -3, which is this one, and -7. Okay. So the person ended up here. So he went here, came back. So this is probably the 98th, 99th step, and this one is 100th step, where he finally is at -3, -7, -3, -7. Okay, so this is just plotting. All we are doing is we are just taking the elements from the list XL and YL. We are doing the plots and just set up some bounds. In this case, this 10. So we are plotting this canvas between -10 to +10, -10 to +10. Okay, that's pretty much it. And then we are doing the grid. All right, now let's do the animation part, right? So that we can actually visually see how the person has moved. Now, for that, all we are doing is, so the animation is simply, it's a collection of frames, right? I mean, any video we see, it's a collection of images, right? Now, in each image or plot, what we are going to do is, so the first plot going to contain the data from first movement only. The second plot, it contains the data of both the first and the second one. And similarly, let's say the 50th frame in the animation contains the first 50 frames movement or the data, right? So at every frame, we are including one more step and we are doing the replotting. Because we are creating animation using all these frames, it looks smooth as if it is a video. Okay. So here all we are doing is, we have this variable called I. Now when we run it first time, I is equal to, let's say, 1. So here we have creating 2 new lists, right? XL2, YL2. So this list will contain only the first 2 elements, right? So only the first 2 steps. For example, the person started here, so he make one move here and the second move here. So when we call this function second time, XL2 and YL2 each contain only 2 values, right? So here we are clearing the plot which was plotted previously, and then we are making a plot, right? So when we call this function the second time in this loop, only from here to here, that portion gets plotted, right? And then we again call the function. This time I value will be 3. So XL2 and YL2 will contain 3 elements. So maybe from here to here, and maybe let's say the person has moved down at this point, right? So these 3 segments get plotted, right? So that way we are generating multiple frames continuously, and we are making that into an animation. Now this is the same stuff. Here I'm just plotting the frame number and the location, right? So we use this animate function from matplotlib. We simply pass this figure, and then this is the function which we have created, animate, where we have the definition, the coordinates, what to plot, etc. And then this one is the number of steps, which is equal to the number of frames. And this one, the intervals, it will determine how fast the frames should move, right? Essentially, this will determine the length of the animation, right? The higher the value, the longer the video, and also for moving from one frame to another frame, the time will increase. Now this repeat means it simply loop after completing all the frames, right? And then finally, if you want to show the videos in HTML, I mean the Jupyter notebook, we use this function. Okay, so this is how it looks like. Okay, so the person has started here. Step 1, he moved in this direction. Step 2 here to the left, and in step 3, the person moved to the bottom. Step 4, the person moved to the left, right? So it goes like this. So here you can see the step number and the latest coordinate. Okay, so this is how the person is moving in time. All right, so it's 100th step, the person is at -2 and 7. So I guess -2 and 7, which is somewhere here. So he visited this coordinate and he went in this direction and he came back, the person. Yes, somewhere here like this. Yeah, so you can see it went and came back like that, right? So let's do one more thing. Let's simulate for a bit more longer to see if it shows interesting pattern. Okay, we simulated for 10,000 steps. This is going to be a static image. Probably this time the bounds will be much larger, so we need to increase the canvas size. So maybe let's increase to 100. The final location, it just happened that this is a coincidence, right? So this is how the person has moved in. Let me remove this ticks, so we don't need these ticks. Maybe to see, let's simulate only 1000 and maybe let's do this 50. So we simulate 1000 steps. Yeah, you can see, right? So started somewhere here in the middle, 0 0, and making this random motion. Let's look at the video. It will take some time, but let's regenerate the video. And also we need to increase the bounds, maybe 40 40. So let's increase the bounds to 40. Yep, so that is generating the animation we will see in a second. So it probably will take 10 times more. Okay, so while the video is being animation is being created, I guess it's clear, right? So I mean, there are different versions. You can simulate. The simplest one would be 1 dimension and a fixed step length. We can generate this in 3 dimension as well. And the step length also don't have to be this discrete. It can be continuous as well, which is what happens in real world applications. For example, the disease spread, the stock market price, the molecules moving in liquids and gases, etc., etc. It's taking quite long. All right, we'll wait for maybe a few more seconds to see if the video is created. Otherwise, we'll stop it there. Now, let's see what sort of questions we can ask, right? For example, the probabilistic questions. We can ask questions like, hey, what is the maximum distance the person can travel in 100 steps, right? What is the maximum distance the person will travel within 100 steps? Or maybe what is the probability that the person will travel a distance of X from origin? So that's not the total length the person has traveled, it's the shortest distance, right? So for example, the person started here and maybe ended here, so it's this distance, right? So it's this Euclidean distance. So what is the probability that the person will travel some n units of distance in, let's say, X number of steps? Okay, so those sorts of probabilistic questions we can ask. All right, let me do one thing. Why is it taking this long? Maybe let me interrupt. Okay, let me reduce the interval. So this time it should be faster. Let me see. Let me just make sure the length of Excel. Okay, we have 1000 steps. That looks okay. We did this. It's taking quite some time. All right. Well, let's do one thing. Because it is taking longer. Maybe we'll just simulate for 100 steps, but we'll do a couple of rounds. Okay. So let's do only 100, but let's generate one more time so that we can see the video. Start and run all. So this time, this is the path it took. So let me do this. I guess my system is out of memory. That's why it's taking quite long. Uh, but I guess you understand, right? And in case if you want to see longer animations, I can create a longer animation and post here. So here you can see, right? So the person started from here, somewhere here, 0. As you can see, this time the video has moved faster because the time gap between the frames we have reduced by 10 times, right? Yeah. So that's how it looks like. That's all for today. In this video, we will learn how to compute integrations using Monte Carlo simulations. Okay, uh, we might have a function f of x, and we want to integrate between a to b. Now, in some cases, we can compute the integration of f of x, and then we can apply the limits, right? But it might, in some cases, this function f of x might be too complex to compute the exact integral. Or maybe even if you are able to solve this analytically, it might take too long to compute the exact solution, right? So in such scenarios, we can use Monte Carlo simulations to compute the numerical integration. Now, we are not going to look into the proof of this derivation, but all we need to do is we sample a number of points between the limits a and b, and we compute the function value f of x, and then we take the sum of the f of x values we computed, and then multiply with this factor so that we can approximate this integral. Okay, so let's start with a very simple example. Let's say we have a function f of x, which is x to the power 2 minus 2, x squared minus 2, and we want to integrate between 2 and 4, right? So this is how the function look like. So this is x squared minus x, and we want to integrate between 2 and 4. Essentially, we want to compute the area under this curve, right? Area under this curve within this limit 2 and 4. So we want to compute the area of this region, okay? This region. All right. Now, because this f of x is so simple, we can compute the exact integral, right? So x square integral would be x to the power of 3 over 3, and then minus x integral would be x square divided with 2. Okay, so let's call it the g of x. Now, the exact integral would be, when we integrate the function f of x between, we want to integrate it between a to b, right? So that would be g of b minus g of a. So the exact integral would be 12.666, right? Okay, now let's see how we can compute this integration using numerical simulation. It's very, very simple and straightforward. So as you know, in Monte Carlo simulations, we do this repeated sampling, right? So let's say we want to take 1000 samples. And so here we are looping over that samples. Now for each time, we are generating a random number between A and B. So within this limits A and B, we are generating a random number with uniform distribution, meaning the random number is equally probable. So any number between 2 and 4 is equally probable. Okay, so we get the random number, and then we simply compute our original function, right? So we are simply passing that random number to the function, and we are computing the function value using this function. So x squared minus x. Okay, so we repeat this process many number of times, and each time we compute the function value and add that to the integral, right? So by this time, we have essentially computed this part. So we have computed the summation over n number of points randomly and uniformly sampled between A and B, and we computed the function and we took the sum. Okay, and then in order to calculate the integral, we just need to multiply with this factor, right? It's the b minus a, so the upper limit minus lower limit divided with the number of samples we took. Okay, so the approximate integral comes out to be 12.53, whereas the exact integral would be 12.66. Now, by integrating this number of samples, we can increase the accuracy. So let's do for maybe 10,000 points. So as you can see here, now this value is a lot closer to this one compared to 12.5 something we got earlier. Okay. Now, often in such scenarios, we want to compute the confidence score or the standard deviation, right? So in such a scenario, what we do is we simply repeat this whole thing many number of times. So let's call this one experiment. So in one experiment, we took 10,000 samples, right? Now we can do multiple experiments so that we will have multiple answers, and for those answers we can take the average and the standard deviations, etc., so that we have the distribution of the answers as well, right? So here we are going to perform 10,000 experiments, and each experiment consists of 1,000 samples. Okay, this time because we have a number of experiments, we have integral list where we are going to compute all our integrals, right? So this part we have seen before. Here all we are doing is the integral we computed for each experiment, we are storing it in a variable called integral LST. Okay, and then finally we can simply take the average and the standard deviation. So as you can see, this average value 12.667 is much closer to this value, right? I mean, if we approximate this to 3 decimal places, that would be 12.667, which is exactly what we have got here. Okay, and the uncertainty or the standard deviation is 0.18. Now if you want to look at the distribution of these integrals we computed over 10,000 experiments, this is how it looks like, right? So in this code, all I'm doing is I'm just taking the histogram, and then I'm taking the histogram, and then we are also plotting the mean of the integral along with the standard deviation, so 1 sigma. Okay, so this is how the integral distribution look like. As you can see, most of the integrals are concentrated around this mean value 12.6, so somewhere here, and we have a standard deviation of I guess 0.18. so from here we have this left this width 0.18, and this width we have 0.18. so 70%, 68, about 68% of the values lie within this 1 sigma range. Okay, now in this one we have used a very simple function so that we can analytically calculate the integral, and we can verify how good the numerical approximation is with the exact value. But this can be really complex function which might not even have an exact analytical solution. Okay, that's all for today. Thank you very much. Hi friends, let's solve a puzzle and also learn a very useful problem solving technique called numerical simulations. The puzzle is this. Let's say we have a house with 4 rooms, 1, 2, 3 and 4. Now from every room we can go to the remaining 3 rooms. So let's say this is a door, and this is a door between room 3 and 1, and similarly this one is the door between room 4 and 1. Now on day 1, let's say the pet is in room number 3 and it makes 1 move per day. We wanted to know where the pet is likely to be after 10 moves or 10 days. Okay. Now from each room to every other room, there is a certain probability of making that move. For example, when the pet is in room number 3, the probability of it moving to room number 1 is 0.3. Okay. And similarly, from room 3 to room 2, it's 0.5. Now let's say the pet, it won't stay in the same room for more than a day. So it will make a move to a different room. So the probability is 0. And then moving from room 3 to room 4 is 0.2. Okay. So these are the 4 probabilities we have. So from room 3 to room 1, 2, 3 and 4. Now the important thing is the sum of all these probabilities should be equal to 1. Now if we want, we can say there is certain probability that the pet will remain in the same room, right? So in that case, we can set this to a finite value. For example, let's say we set it to 0.1, and then we would have to modify the other 3 numbers so that the sum is still equal to 1, because that's the total probability, right? All right. We are going to solve this problem using 2 techniques. All right. The NumPy, and similar to how we define the probabilities from room 3, we define the probabilities from room 1. So when the pet is in room 1, what are the probabilities of moving it to room 2, 3 and 4, right? So here we have that probability of moving from room 1 to the remaining 4 rooms. Similarly, from room 2, and this is what we just saw, from room 3 to the remaining 3 rooms, and finally room 4. Now if you see, we set all the diagonal elements, which is the probability of staying within the same room, we set it to 0, but it's not necessary. I mean, as I said, you can define, you can give it a finite probability, but you have to make sure that the sum of each row is equal to 1.0. All right. So let's solve it using this numerical simulation method, which is widely used in science, engineering, and many areas really. All right. So I'm sure you are probably aware of the NumPy random function. So here we have NumPy random choice. So when we define like this, all these 4 numbers, we are denoting these 4 numbers to denote the rooms 1, 2, 3, 4, right, are equally probable. So for example, if I run this function, let's say 100 times, it is likely that 25 times I get 1 as the output, 25 times I get 2, 25 times I get 3, and the remaining 25 times I get number 4. So all 4 are equally probable. Now we want to make use of this function to simulate this process, right? But we know from room 3, the probabilities are not equally distributed to all the remaining 3, including the room itself, right? So if it is 25% probability moving from room 3 to 2, 3 to 1, 3 to 4, and remaining within room 3, then we can make use of this function to simply sample. So the pet is in room 3, where it is likely to move. Just run this, and whatever you get, that would be the answer, right? So from 3, it moved to room number 2. But we know we do not have the equal probabilities. So what we do is, to this function, we can also supply the probabilities. Okay. So 0.3, 0.5, 0 and 0.2. Now when we run this function, what happens is, NumPy random, it generates a random number between 0 to 1. All numbers are equally probable. Now, if the generated number happens to be between 0 to 3, it will return 1 as the answer. Whereas, if the generated number happens to be between 0.3 to 0.8, it will return 2 as the answer. Now, where is this 0.8 coming from? This is simply 0.3 added to 0.5. Okay. So we have, basically we are dividing the total probability between 0 to 1 into 4 bins. So the first bin is between 0 to 0.3. Second one is 0.3 to 0.8. The third one, which I have not written here, but that's between 0.8 to 0.8. Okay. So that will never happen. And finally, if the generated number happens to be between 0.8 to 1.0, it will return number 4. So that means the cat or pet likely to take or move from room number 3 to room number 4 if the generated number happens to be between 0.8 to 1.0. So we make use of this function to simulate this whole process. All right. So if I run this function, let's say 10 times, 50% of the time, which is 5 times, we are likely to get number 2 as the outcome. As you will see, the 2 is the more common one. The least likely one is number 4 because it has a probability of only 0.2 or 20%. And we will never get room number 3 because its probability is 0. Once the cat is in room 3, it has to move to one of the other rooms. It does not remain in the same room because that's how we defined it. Okay, so those are the basics. Once all those concepts are clear, simulating this problem is super easy. So here we define a function, simulate pet path. It takes this transition matrix, this one, that's the technical name for it. It's called transition probability matrix, but it doesn't matter. So it takes that matrix. It takes the initial starting room. Now on day 1, here we put the pet in room 3, but it could be in any one of the rooms, right? So we can define that. And the number of steps or the number of days, after how many days we want to find out the pet, right? All right. So to begin with, the current room is the start room. And here we define a path. So we are going to see at the end of the 10 steps, what is the path taken by the pet. So for that, we define this variable path. And initially, it's the current room. And here we are simulating it for the chosen number of steps, 10 in this case. We are just calling this function. Okay, we are just calling this function. Here we hard coded the probability for room number 3, right? The current room. So what we are doing is here we are just dynamically updating the current room so that the appropriate probabilities are used when sampling or figuring out the next room. Okay. All right. So we find out the next room. We add the next room to the path and we update the current room. All right. So we run the loop for 10 times. So here we said, we want to simulate it for 10 steps or 10 days and the starting room is number 3, right? All right. So we do the simulation and we get this path back. So here we have the path. We are just printing the path. So what happened is on day 1, the pet is in room number 3 and it moved to room number 1 on second day. And then it moved to room number 3, so on and so forth. And finally, after 10 days, the pet is in room number 2. Okay. So does it mean, is it always going to be in room number 2 after 10 steps? The answer is no. This is only one of the likely scenario or one of the possible scenarios, right? Because at every step, we used probability to find out the next room. Now, if we run this again, we might get a different answer. For example, I run it again. So this time, again, we are starting the pet from room number 3, but this time it ended up in room number 3. So does it mean we cannot answer where the pet is likely to be because it seems completely dynamic? We don't know. Every time we run, it seems like it's going to be in a different room. What we can do is we can repeat this experiment many number of times. For example, let's say we have 1,000 houses. We put 1,000 pets in room number 3 and we observe where the pet ended up after 10 steps. And from those 1,000 experiments, we take the final room and we compute the probabilities for it so that we answer this question in terms of probabilities because it's not going to be absolute. Okay. because we can never say that it will be in room number 1 or room number 2. What we can say is, hey, there is 70% chance that it will be in room number 1 after 10 steps. There is 30% chance it will be in room number 2. There is no chance it will be in room number 4. So we can answer this puzzle in terms of probabilities only. Okay, that's what we are going to do. All right. So here what we are doing is we are repeating the same experiment 20 times. Okay. So here we have a new variable called final rooms. So what we want to do is we want to repeat this experiment and we want to collect the final room. All right. So do the simulation for n number of times, calling the same function, and we are collecting the final room from the last element. Okay. All right. So here we have the results from 20 simulations. So every time the cat start from room number 3, it took some path and finally ended up in room number 4 in the first 3 experiment, but in room number 3 in the 4th experiment, room number 1 in the 5th experiment, so on and so forth. And if we collect the final rooms, this is how they are, right? So these final room we have collected here. But simulations, we repeat hundreds of thousands of times, so that the more times we repeat, our approximate solution will converge to the exact solution if we can solve this problem in an exact manner. We will see that also. So what we do is, here we are running it for 1000 times, exactly the same thing. But once we collected these final rooms, all we are doing is, hey, out of these 1000 experiments, how many times the pet ended up in room number 4? Do the compute or count how many times it ended up in room number 3, 1 and 2. And simply divide those numbers with the total number of experiments so that we will get the probabilities. Okay, so that's exactly what we are doing here. So our final probabilities or answer to this puzzle is that after 10 step, the probability of the pet to be in room number 1 is 0.21. Okay, for room number 2, 0.3, for room number 3, 0.34, and finally 0.14 for room number 4. So to answer this question, after 10 step, the pet is more likely to be in room number 3 and least likely to be in room number 4. So there is double the chance that it will be in room number 3 compared to it will be in room number 4. Okay, so the final response is also in terms of these probabilities. Okay, so that's the numerical simulation approach we took. And the second one, exact analytical method. So this problem is actually so simple that we can solve it analytically. So we already saw we have a transition matrix and we have the initial state which is where the cat originally are on day 1, which is this room number 3. So 0, 0, 1, 0. Now, yeah. So here we have a transition probability matrix, but for 3 rooms. Okay. So this pi 1, 1 that represent probability of moving from room 1 to 1. From 1 to 2, 1 to 3. Okay. So let's imagine we have only 3 rooms. So here we have a 3 by 3 matrix. Now let's just multiply this matrix by itself, or we are taking the square of this matrix. Okay. When we take the square, we get the result like this. Okay. Let's closely examine what this element actually means. So here we have pi 1, 1 multiplied by pi 1, 2 plus pi 1, 2, so on and so forth. Now what this is saying is the cat, this is the probability of moving from room 1 to 1 multiplied by probability of moving from room 1 to 2. So what it means is this element represents the probability of moving from room 1 to room 2 in 2 steps. In the first step, it remained within the same room. In the second step, it moved from room 1 to 2. Similarly, this represents the same probability, but this time the cat moved from room 1 to room 2 in step number 1, and in step number 2, it remained within the same room. Here is another possibility that it go from room 1 to 3 and then from 3 to 2. Okay. So all these elements are simply representing the different possible ways of going from room 1 to room 2. Okay. So room 1, room 2. So as you can see, it's always start at 1 and end at 2. So we are looking at the first and the fourth element here. 1 and 2. 1 and 2, 1 and 2. So this term represents, these are all the possible ways of going from room 1 to room 2 in 2 steps. Okay. Since we took the square of this matrix. If we take the power of n, this element represents the different ways of moving from room 1 to room 2 in n number of steps. So the intermediate steps can be maybe 1 to 3, 3 to 2, 2 to 1, again 1 to 2, right? So we would have, in the first element, we would have pi 1, and in the last element, we would have pi this 2, the fourth, this element, right? So by multiplying this transition matrix by itself n number of times, each element is simply representing all the ways of moving from a certain origin to a certain destination in n number of steps, n being the power of this matrix. Okay. So what it means is, we simply take the power of this matrix with the number of steps, which is 10, and we multiply that with the initial state. That will give us the final state. Okay. So our initial state is this. We simply took our transition probability matrix and then took the power of number of steps, which is 10. And here we have the final state. Now, if we are simply printing this final state, which will have 4 numbers, which are the probability in each room after 10 steps. Okay. So here we have 0.2, 0.3, 0.35 and 0.14. This is the exact solution. So if you go back, this is our simulated solution. Sorry. Yeah, this is our simulated solution. Now, here we have run this experiment 1000 times. The more number of times we run this experiment, these 4 values get closer and closer to these 4 values. Okay. So in simulation, we find this approximate solution, but the more times we repeat this simulation, the solution will approach to the exact solution. Okay. So that's our final answer. I hope you like this puzzle. Now, if you are into probability and numerical simulations and solving a variety of problems using similar techniques, I have a mini course. I provide the link in the description. So it starts with very basics of probability and how to compute the probabilities using simulations, etc. Okay. So please check out that course. That's all for this video. Thank you very much.